part A wants us first of all to describe how to do that step. So that's a cycloalkane, so remember it behaves just like any other kind of alkane, which means that you need radical substitution to get the halogen in there. So it's a reaction with chlorine gas, and you need UV light is the key condition. So that's all you need to say as far as the reagents and conditions are concerned. That word reagent, if you didn't know, it means the substance that you add to react with it. So chlorine is what it meant by that. The mechanism of reaction involves homolytic bond fission. It's one of those things that's just kind of annoying to put into words, but you've got to make sure you phrase it carefully. So it means that when a covalent bond breaks, one of the electrons involved goes to one of the atoms that was participating in the bond, the other electron goes to the other atom that was participating in the bond. So really spell it out, make it clear like that. So it's breaking a covalent bond where one of the electrons goes to one of the atoms that was involved in the bond, the other goes to the other atom that was involved. Okay, so that's that one. So then we've got to write down the propagation reaction. So remember, the first thing that happens in initiation is that you get chlorine radicals, and then the propagation steps involve a chlorine radical reacting with the alkane, which is cyclohexane. Normally we use molecular formulae in describing these radical mechanisms because it's just easier to see what's going on and keep track of the hydrogen. So I think that's the best way to do it. So the chlorine atom radical comes along and it grabs one hydrogen out of there, so you get HCl, which is the first product of the reaction, and it generates a new radical, which is C6H11 now, because it's had a hydrogen taken away, and that's now a free radical. So we put a dot there. I usually put it at that end just to emphasize that it's one of the carbons that has the unpaired electron. So that's the first propagation reaction. So this radical now is going to come along and react with what it bumps into, and in the second step it bumps into another chlorine molecule, and again it just takes one atom out of the thing it bumps into, so it will take one chlorine out of the Cl2, which gives us C6H11Cl, and it leaves us with another chlorine radical. And those are the two propagation steps, and you can see the way it works, that this chlorine radical then feeds back into that step, and so it goes on and on in a chain reaction. But that was all you needed for the marks there. The next thing it wants is to know what happens if two chlorines get substituted into the ring to make dichlorocyclohexane. And all you really have to remember that is that each time a chlorine goes in, an HCl is produced as well. And so long as you remember that, then it's easy. So cyclohexane, it says to use molecular formulae, so we've got to use C6H12, and it's going to react with 2 moles of chlorine to give you dichlorocyclohexane. So remember, the chlorines go in replacing hydrogens. So if we've got 2 chlorines in there, we've got to have 2 fewer hydrogens. So C6H10Cl2 plus 2 HCl. Okay, so if you remember the pattern, however many chlorines have gone in, you get that many HCl's formed, and therefore you need that many Cl2's reacting. It's quite straightforward, but if you don't learn it, you can come unstuck. Okay, then in part B, it wants to know what happens in steps 2 and 3. So obviously the complication here is that it doesn't tell you what goes in the middle there, but the key thing is looking at the end and thinking, well, that's a ketone, and I only know one way to make a ketone, which is oxidation of a secondary alcohol. So this basically has to be the secondary alcohol, because that's the only thing you know which can be converted into a ketone. So we put that in there first, and that gets us 1 in the marks. And then you think, right, how do I turn a halogen into an OH? And that's the nucleophilic substitution reaction. So for step 2, we need sodium hydroxide, and it must be aqueous. That's very important. If you just write NaOH, you probably wouldn't get the mark, because it must be an aqueous solution for that substitution reaction to happen. And then step 3, well, that's the oxidation of an alcohol to a ketone, and so that is aqueous acidic potassium dichromate is the reagent for that one. Okay, so you can see those kind of questions, it comes down to learning what reagents you need, what key conditions you need, like the aqueous solution there, the acidity in the aqueous solution here. And that's a very big chunk of organic chemistry. So try, as you go through, to train yourself to learn reagents and conditions, and then you won't have too big a job at the end. If you think, yeah, I can't be bothered to learn all that now, you're going to have a massive job learning all those things at the end of the second year. Now we come to the percentage yield calculation. So it's saying across all these steps, the overall yield starting from here and ending up there is 68%. And it's saying, that being the case, if we want to make 1 kilogram of the final product, cyclohexanone, what mass of that do we start with? So the first job, of course, as always, when you've got a mass involved, is to turn it into moles. So that's the first step, is to get the moles of cyclohexanone, is mass over mR. And it's 1 kilogram, which of course you know is 1,000 grams. Need to turn it into grams to do that. Add up the mR of that molecule. Just be careful counting the hydrogens, because obviously in a skeletal formula they're not shown. So that's C6H246810. Okay, no hydrogens on that one. So C6H10O, which adds up to 98.0, and 1,000 over 98 is 10.20 moles. So then it's saying, okay, that represents 68% of what we could have got if the reaction had gone perfectly. So the next job is to say, well, if 10.20 is 68%, what's 100%? So we get that the moles of cyclohexane needed equals 100% of the number of moles we could have got, because you can see 1 mole of this goes to 1 mole of that. So we've just got to scale up from 68% to 100%. So it's 100 over 68 times 10.2 moles. Okay, which is 15.01 moles. Okay, so make sure you can see why we did it that way. That we said, right, this number of moles, which is what we actually need to get, that will only be 68% of what we could have got if it had been perfect. And what we could have got if it had been perfect would be the same number of moles as the starting material. So we scale up, multiply by 100 over 68 to work out what 100% of the possible moles would be, and then say, right, that's the same as the moles of cyclohexane. So we've got that number, and then all we need to do is to turn it into a mass. So we get mass of cyclohexane is moles times mR, which is 15.01 times 84.0 for C6H12, which is 1,261 grams. But you have to read the question carefully. It says give your answer to 2 significant figures, and you can see why it says that, because the percentage yield was only 2 significant figures, so those are the only meaningful ones. So that needs to round up to 1,300 grams. And that would be the correct answer.